The discovery of exoplanet is now more important than ever as humanity faces various threats to our own planet, such as asteroids, which are constantly moving towards Earth at a high speed, or some internal factors like air pollution, constant earthquakes, or floods. In 2009, NASA launched the Kepler Telescope, a space observatory specifically designed to search for exoplanets in the Milky Way galaxy. The Kepler Telescope uses advanced lens and onboard computer system to scan the stars for any dips in brightness that would indicate the presence of a planet passing in front of it. The Kepler mission was highly successful, discovering thousands of exoplanets and providing evidence that Earth-like planets are common throughout the galaxy. In 2018, the Kepler mission was replaced by the James Webb Telescope, which is even more advanced and capable of searching for exoplanets even in deep space. The continued search for exoplanets is vital for understanding of the universe and the possibility of life beyond our own planet. With different policies and meeting at a global level, different space agencies and governments from throughout the world have discussed for a need of exoplanet. What we have come up as a solution is just a simple policy, and that is if we will discover exoplanet, no country owns it. But one of the biggest questions arises, are we really gonna find an exoplanet? Are we really going to settle down there? While living in the 21st century and tracking an exoplanet manually is inefficient and time consuming, also the probability of locating the planet decreases. Analyzing billions, if not trillions, of data manually from the telescope is tiring and less effective at the same time. Living in the world of computers gives us immense power to reduce the search time by writing some simple codes, but integrating artificial intelligence to a code increases the probability of finding an exoplanet by 900 times and is more effective. To understand how scientists locate exoplanet, we need to understand a simple concept known as transit photometry. Transit photometry is nothing less than observing the brightness of a star as the planet passes in front of it. By observing a star for long duration and seeing a repetitive trend in the drop of brightness can help us locate an exoplanet. Recently, I attended an amazing scholar program known as Inspirit AI, where we created our own machine learning algorithm to locate an exoplanet. I worked with a group of 5 students and we were able to locate 27 exoplanets with an accuracy of 99%. Inspirit AI is a perfect platform to enhance your creativity and develop skills on AI. From printing Hello World in Python to customizing your own neural network model, Inspirit AI has covered it all. Learning about different problems throughout the world or learning about neurons, we were taught each and everything from scratch. The instructors were students or graduates from top colleges such as Harvard or MIT. We also got an opportunity to learn about the college application and what college really looks like. We also learned about ethical concerns of AI and how to write an effective college essay. What you would be seeing next is the presentation from our team, presenting our work in front of a large audience. We had spent approximately 15 days with over 40 hours to make this project successful. Josh, Aiden, Noor, and I, Aditya, are excited to present our project to you all today. Next slide, please. We have structured the presentation into three main sections. Firstly, we will discuss the significance of a project and the principle it is based on. Next, we will present the various data and machine learning models we used during the course of a project. Finally, we will move on into ethical consideration, real world application, and future possibilities for finding eco friendly planets in space. Next slide, please. So, why do we need to search for an exoplanet? Today, as we all know, we are constantly looking for a habitable planet due to different factors. One of the major reasons is to locate exoplanet, which can be further classified into habitable planet or not. Next slide, please. Now, moving on to the principle it works on, transit photometry. Next slide, please. A technique used to measure the dimming of a star's light as a planet passes in front of it involves continuous monitoring the brightness of a star. By measuring the depth and duration of the transit, we can predict if that's an exoplanet or not. On the diagram, you can see a dip between label 2 and 3 as the planet passes in front of the star. Next slide, please. We are using data from Kepler Telescope to train our model. Next slide, please.
Okay, data augmentation we used. Next slide, please. What is data augmentation? In this case, it's changing the data in order to better suit the model that we use and making it more accessible. Why do we need it this time? There's a large range of brightness for each star, and there's a lot more stars that don't have exoplanets opposed to stars that do have exoplanets. Next slide, please. Normalization was our first method of data augmentation. This is a method of dividing every number in the list by the highest number in order to get a value from 1 to 0. It's used for when there's a very large range like we have for brightness, and when you have it from 1 to 0, you can now use logistic regression. Next slide, please. All right, small, which is the second type of data augmentation, is another type. Instead of dividing, you create more data. So you create more data by drawing a polygon around the existing data, like as seen in the photo, and then putting extra points around on the diagonals or on the sides of the polygon. This can be helpful in just providing more data, since we only have 37 exoplanets and over 5,000 non-exoplanet stars. But it can also have some disadvantages because it can create patterns that aren't really there. Next slide, please.
Okay, so I'll be taking you guys through the models that we used. Next slide, please. So the first model we used is the KNN model, which is called the K-nearest neighbors classifier, and it's when we have an unknown example and we make a prediction based on what it's closest to. An example is there below. So we have blue circles and orange circles, and when k is equal to 3, it'll group to 3 circles surrounding the star, which is the new unknown example. And here, because we have more orange circles, we'll classify the star as an orange circle class B. So here we have the pictures of the confusion matrices and our accuracy after using the KNN model. So 0 is considered classifying as a non-exoplanet, and a 1 is an exoplanet. So in this example, it's saying that in the training model, 5049 is considered a non-exoplanet, and the 1 is just the one that they classified wrongly. And overall, throughout this entire training and testing model, we can see that they classified almost every single model as a non-exoplanet. And even though the accuracies are high, it's still not doing what we wanted, because we wanted to classify the exoplanets correctly. Excellent. So another model we use is the SVM classification. It's called the support vector machine model, and it creates a line or hyperline to separate the model into two different classes, as shown in the image below. And in this model, it's actually very similar to the KNN model, except I consider it the more extreme version, because it classifies literally everything as a non-exoplanet. So defies the point of this model. And again, the accuracies are high, but not doing what we wanted to. Next slide, please. Our third model is the logistic regression model, and this predicts a category based on probability. It uses an S-curve to determine a number between 0 and 1, as shown in this image. And our confusion matrices here, it's classifying the exoplanets much better, as here in the training model, we have 0 wrong answers in the exoplanets, and in the testing, we just have the 1 wrong, but it's getting most of it correct. And here the accuracies might be a little low, but it's correctly classifying the exoplanets. And all these 3 models, it's used with non-augmented data. But using the augmented data that Aiden explained to us earlier, it could produce much better results.
So I'll be going through the real-world impact of AI when applied to astronomy, which includes ethics, application, and future directions. As you may know, according to a report by the World Economic Forum, 85 billion jobs will be replaced by AI by 2025. Now, within the context of AI applied to astronomy, some questions to ask are, who should we blame for incorrect result? The programmer, the person who took the image, or the astronomer who identified it? And will AI even replace astronomers? And since 1995, there have been over 5,000 exoplanets discovered. Research scientists right now are using detection and characterization methods with AI, an instance of which being a machine learning model that was developed from data collected through NASA's Kepler Space Telescope, which has actually uncovered 50 exoplanets. These included those that are potentially habitable for humans. AI is certainly going to make a huge impact in this field for hunting for exoplanets, with methods such as studying the star's variation over time becoming even more advanced and accurate. Now, as for what the future holds in this space, research scientists and astronomers alike hope to use AI for current and future telescope missions, as it can provide a consistent and efficient method of validation. And it's based on machine learning, so it can be improved upon and can continue to become more effective with each new discovery. AI, at the moment, only 30% of all known planets were validated with only one single method. What can be done to classify more? If you can guess, please write your answer in the chat. Otherwise, that's us. Thank you.